So with the introductions to set the expectations, let's dig into the solutions. We initiate the direct repair of the scan data by using the polygon modeling tools to directly repair the actual scan data and recreate the missing pieces. We start this example by first importing the scan data into NX. As this session is run natively, the scan data will be located in the company's scan data folder. We select the input from the scan process. Here the input will be the specific STL file. As you can see, the result is a convergent body that will be represented in the feature list and possible to incorporate in your continuous downstream processes. As the scan contains the cap area of the actual crack and missing piece, we start by removing the cap area as this is not needed and will be wiped out by the actual repair. By using the polygon modeling snip function, we will divide the convergent body along the crack and missing piece edge. By utilizing a combination of the polygon modeling smart selection rules, we can easily define along what edge we would like to divide the convergent body. Here we will be utilizing a combination of the selection rules, tangent facets, rough brush, and flood fill. In the radii area here, we can see that the tangent facets does not quite pick up, and the flood fill would therefore select the entire convergent body. We therefore set the selection rule to rough brush and manually define the boundary edge. Once selected and the boundary facets clearly defined, we switch to flood fill and finalize our selection. Hitting OK will now divide the convergent body into two according to our requirements. As we no longer need the cap area, we simply delete it. To clearly see the damage to be repaired, we extract the edge curve of the convergent body and color it red for clarity. Since geometry is missing, we use the existing geometry bits in the direct connection to the damaged area in order to create some support geometry. Here we once again use snip to create a copy of the top of the axle outlet to create a limited copy of the area that we will reuse. The additional copy we will get when performing the snip operation. With the copy option on, we simply delete as we do not need it. The remaining convergent body of the top of the axle outlet is rotated so that it fully covers the gap and missing area. By again using snip and the option remove selected, we remove the excess bits or material of the convergent body so that it can be incorporated into the final convergent body that we are repairing. Here we use a combination of selection rules such as rough brush and flood fill. The remaining bit is smaller than the hole to fill, which is fine as we will be using the polygon modeling command merge disjoint to combine the two convergent bodies into one. To merge the bodies, we simply select the two bodies to participate and along what portions of the edges on respective body the merge will be executed. With the support geometry in place, we can now smartly start to fill gaps and holes. We start by closing the rim surface by bridging the gap. This is executed by using the fill hole command and utilizing the option bridge gap. We do one side at a time in order to control the edges. We also do the center bit separately in order to control the inner sharper edge shape. To fill the larger missing chip area on the exterior, we will first use bridge gap in the axial direction to fill the main area and to maintain the curvature shape of the cylinder. We continue by creating the local transitions around the sharp corner areas by using bridge gap option in order to control the sharp corners when executing the final fill hole operation. We of course repeat for all the sharp corners on our design. When we now have control over all the sharp corners of our design or repair design, we can now use the fill hole option to simultaneously fill all the remaining holes. Depending on the hole characteristics, we can now set various transitional constraints or smoothness. Here we will try tangent based to start off with. When selecting the holes and filling them, we note that the tangent base does not quite fit our purpose and create a bump if it would be accepted. We therefore change the smoothness to refined and find a better result. Once we have selected all the interior holes, we continue by including the exterior holes as well. When inspecting the result of the fill hole operation, we notice that there is kind of a bump on the inside of the axle outlet and bearing seating area. This is due to the fact that we never created the actual bridge fill like we did on the exterior. This does not exist on the exterior side as we did it in a better way there. We could of course fix this area, but we are satisfied with the result as it is for now. As you might have noticed, there are still two small holes on the rim. I have intentionally left those out just to show you that the convergent body is currently a sheet body. We fill those two small last holes by using fill hole and check again to see the state of the convergent body. Sectioning it again shows that the convergent body now is a solid body, as expected. This wraps up the first section of this session, where we quickly have digitally reverse engineered a damaged section of a physical part and directly have repaired the design by using NX and polygon modeling. In many cases, this will be enough. However, in some cases, more accuracy and the ability to parametrically modify the design is required. For this, please follow us into the next part of this session. This concludes the polygon modeling section, that is the second in the series of total 3 tutorials handling reverse engineering on the NX platform.